Thank you so much for coming to my talk. My name is John Dios, and I am CTO of SlamData. SlamData is a company doing NoSQL analytics in a 100% purely functional style using the Scala programming language. And we've been going at it for about 3 years now. I'm happy to say we just raised our second round of financing, $7 million worth, which means a lot more open source development written in purely functional Scala programming. I'm here today to talk to you about one of the projects I've been working on in my company, and that is QUARK. QUARK is a purely functional Scala DSL for data processing and analytics. And today, I hope to show you that purely functional programming can be not just practical, but give you amazing capabilities beyond using Scala as a better Java. Apache Spark. How many people have had the pleasure of using Apache Spark? Pleasure. Wow. I'm joking, of course. 7 years ago, though, I remember Berkeley Data Labs coming out with Spark. And I hopped on over to the repository and I took a look at 7,000 lines of Scala code. And those 7,000 lines of Scala code made it possible to write an implementation of the famous word count application in like 10 lines. And I was blown away because I had been from the school of MapReduce jobs in Java programming. And I looked at that and I said, there's something here. There really is something here. Apache Spark, what it did is it took some functional concepts and it applied them to big data processing, and it changed the world forever. Fundamentally, what Spark is it's a very fast and general purpose engine, and by that I mean it crunches numbers, for doing big data processing. And of course, it has built-in modules for things like streaming, SQL built on top, machine learning, and graph processing. And there you go. There is the world-famous example of how you do a word count in, really 2 lines of code. Pretty amazing. But let's face it, Spark sucks. It's functional-ish. It takes a few good pieces of functional programming. But there's still exceptions, there's still typecasts, there's still lots of null, there's tons of mutation. There's this big global thing hanging around your program called Spark context. It requires all your code be serializable, and as a result, will probably pull in your entire program at more than one point in your debugging process. You can create type-safe programs that go wrong because semantically they don't make any sense. It has second-class support for databases, so if you try to use Spark on a non-Spark or Hadoop environment, you're going to find it doesn't actually push much computation into the underlying data store. It only pushes a little snippet of a where clause, and the rest it has to pull back into its in-memory cluster for crunching the numbers there. Dependency hell. How many dependencies does Spark have? Who knows? We've lost track of the number of dependencies Spark has. We know it's a lot because the size of the jars are measured in gigabytes. And it's super painful to debug Spark applications. How many of you have written counts all over the place to find out what went wrong and where? And just little random stuff like that, trying to debug your Spark program. Yeah, exactly. And then finally, it has implementation-dependent performance. And what I mean by that is you have to be very aware of things like garbage collection and number of partitions and GC tuning parameters and all sorts of things that in an ideal world, like functional programming is supposed to be declarative, right? You shouldn't have to keep track of all that. You should be able to write a Spark program, and no matter how many different ways you write it, it should end up being expressed as a low-level computation that is independent of the way in which you wrote it. That's the property of declarative systems. So you may be thinking, why does Spark have to suck? And the answer is, well, computation. So when you build a Spark program, you feed it Scala closures, which are opaque blobs of code. It has no way of knowing what's inside those. And as a result, it has to serialize them and send them over the wire. That's why you have this big, massive, bloated jar being shipped off to the Spark cluster. And it's also why Spark doesn't have the ability to peek inside there and know exactly what you're doing and discover problems ahead of time or optimize certain cases and normalize your program to something that's going to run efficiently. It's because fundamentally, when you are using Spark, you are writing a bunch of opaque blobs of Scala code that the Spark runtime has no insight into. Well, whenever you're running into a problem like this, I encourage everyone to ask, what would functional programming do? What would a functional programming do? Well, ideally, we would have a solution that's purely functional, right? Everything would be a pure function. You give it an input, it returns the same output for the same input. There would be no exceptions, no casts, no nulls, no global variables, no serialization whatsoever, since so many problems in Spark arise from serialization. And if the program type check, then it would make semantic sense and be guaranteed to execute with the intended result, which is a property that you do not have with Spark. It would have first-class support for databases, because why not? Why can't you use the same Scala DSL on Hadoop that you can use on a NoSQL database or even a relational database? It would have very few dependencies. It would have better support for debugging because it wouldn't be dealing with opaque hunks of Scala code. And ideally, in an ideal world, no matter how many different ways you can find of writing the same program, they would all normalize down to the same thing, which is executed with the same performance guarantees. In other words, no matter how you write the program, if the program does something, it will end up being translated into the most efficient way to do that. How would we solve this if we were approaching this from the mindset of a functional programmer? Well, we functional programmers, if when presented with a problem, we like to say, don't solve the problem, describe the solution to solving a problem, AKA the DoNothing Rule. And that makes sense, right? Functional programmers are lazy. Why should we do something when we can just talk about the solution? And in this particular case, what that means is don't compute. That is, if we're building something like Spark and we want to gain all these advantages, we're going to have to sacrifice the ability to compute. And instead, we're going to have to build a description of the computation. And what that means is we're going to end up building a description of a computation that can then be translated, compiled into the instructions supported by a given target infrastructure, whether they be sort of low-level operations in a Hadoop cluster or SQL or low-level code, whatever it might be. Instead of actually trying to crunch the numbers with opaque blobs of Scala code, we're going to use our Scala code, we're going to embed a language in it that ends up building a description of the computation, and that description of the computation will be first class, and we'll be able to do all sorts of amazing things with it without having to serialize hunks of code around the wire. And that brings me to QUARK. What is QUARK? Well, QUARK is a Scala DSL that's built on Quasar Analytics. Quasar Analytics is sort of first of its kind. It's a general purpose analytics compiler. It can take an analytics workflow and it can translate that into any target infrastructure, whether that's a relational database or a NoSQL database or a Hadoop environment. It doesn't have any computational ability by itself. So Spark is a computational engine, but Quasar Analytics is an analytics compiler. And QUARK is a Scala DSL built on top of Quasar. QUARK is quite a bit similar to Spark in the way it looks, but instead of crunching numbers, instead of allowing you to feed arbitrary user-defined code into this framework, it simply presents this DSL that looks like you're building computation, or looks like you're executing code, but it's actually just building a description of a computation. And that description of a computation is later compiled to whatever target infrastructure you happen to be running on. There's the example for word count in QUARK. And honestly, it kind of looks like the example from Spark, doesn't it? We have flat map there, we have map, we have reduce by key using an anonymous lambda. And for all intent and purposes, that's Spark. Only something very fundamentally different is happening behind the scenes. This may look like we're building ordinary Scala functions, and maybe you think these things are being serialized across the wire, but it's not. Every single line here is building a description, a type-safe description of a computation. And at the end process is a description of the entire analytics workflow that can then be translated into SQL or translated into Spark or into a NoSQL database, into any different target infrastructure without any need for serialization. Here's another example of QUARK, where we load a data set, group it by country, map to the age, and then reduce by the average to compute average ages across countries. Again, it looks like Spark, doesn't it? More or less. It's a little bit different, but basically, if you're familiar with Spark, you could probably pick up QUARK in a matter of minutes. Currently, QUARK supports all the targets that Quasar Analytics does, which includes MongoDB, Couchbase, MarkLogic, Hadoop, and HDFS, and it has a very modular architecture for adding new targets. So if you want to support a new target like Cassandra, for example, or Oracle, SQL Server, Postgres, Elasticsearch, whatever it might be, you can just add a new compilation target, translate from the intermediate code that Quasar uses into that backend, and then you'll get support for everything on top of that, including, of course, QUARK. And note that QUARK, unlike Spark, the fundamental basis of QUARK is semi-structured data, which means it can easily handle nested data or non-uniform data, which are things that Spark is not very good at handling. So I'm going to dive into the guts here in a second, but both QUARK and Quasar Analytics are purely functional, 100% open source projects written in Scala, and you can check both of them out on github.com/quasar-analytics. All right, so now let's talk about building a DSL in Scala. There are a couple of different ways we can do it. And the first way we can build a DSL in Scala that would be amenable to a compilation process, like QUARK, is to build a data structure that describes all the operations in our language. And in this particular case, I've created a little mini language representing an expression, and there are two types of expressions in this language. One is a raw integer, and one is an addition of two other expressions. So you can see this forms a tree with the leaves being integers and everything else being addition. And if you have a tree like this, then you can define helper functions that allow you to build a DSL that says add this, add this, add this, and so on and so forth. And then you can take and define an interpret function, which, given an expression in this DSL, gives you the value of the integer. And you can see there it's a two-liner. It's very, very simple. And of course, you can serialize this into JSON or whatever other format. You can deserialize it and so forth. And you could, in theory, compile this. So this is a description of a computation. So you could compile it to JVM bytecode. You could compile it to JavaScript. You can compile it to anything that you want, because there's nothing that is opaque here. When you have an expression, you can pattern match it, introspect it, and you can find out all the different steps involved in the computation. And because you have that sort of complete ability to peer through into the deepest layers of that computation, you know everything that's happening, and as a result, you can compile it to any other thing without having to serialize any type of Scala code. If we want to extend that little language so we can do stuff with more than just integers, then we can just add new case classes, including one that allows you to construct a string expression, and another one, for example, that allows you to concat two strings. It's very simple. We can build up our language primitive at a time and build ever more complex languages describing computations of things involving integers and strings. However, when we extend it in this fashion, we run into a little problem, which is addition is only defined for integer expressions. That is, expressions which evaluate to an integer. And string concatenation is only defined for expressions that evaluate to a string. How are we going to solve this problem? We're going to introduce a phantom type parameter. And that phantom type parameter is going to essentially be an embedding of Scala's type, or rather the type of this expression into the Scala type system. So we're going to have an expression that computes an int, for example, by using that phantom type parameter to represent int. Or we'll have an expression that computes a string by using it to represent a string. And by using this phantom type parameter, we can suddenly make the addition and string concat cases well typed, because we can restrict the types of expressions that you can feed to them. And then you can see we can define an interpret function, as shown there, very simply and in a type-safe manner. When you do this, you will have utilized a feature known as generalized algebraic data types. So we've gone from using algebraic data types, which are simply sort of sums and products, to generalized algebraic data types in which the compiler has awareness that certain constructors in a sum type must utilize a given type. So for example, the integer constructor here, if you match against that in the interpret function here, Scala knows the type A parameter must be int, because that's the only way you could have constructed an integer, is with the type parameter A equal to int. It's a way for us to allow Scala to carry a type level equality around during the computation process, so we can prove things about the way these different terms in the sum were constructed. And if that doesn't make sense, don't worry about that too much. But if you try to write this, you'll appreciate that Scala has decent support for generalized algebraic types. Unfortunately, this support is not yet perfect, and there exist numerous bugs in Scala's support for generalized algebraic data types. I found 3, but it's possible there are others, and I know there were some that were fixed. Friends don't let friends use GADs in Scala, basically. So if we want to achieve the benefits of GADs without running into all these edge cases in the compiler, how are we going to do it? Turns out there's a solution, and it's very simple. It's called finally Tagless. In finally Tagless, instead of building a data structure, we build what amounts to a type class that describes the operations supported by our DSL. In this particular example, I have an expr class, which is going to give me the same 4 operations, one to construct an int, one to construct a string, one to add 2 ints, one to concat 2 strings. And it's going to be generic in the type of data structure being used to represent this expression. And then I can define a trait called DSL, which is going to say, given any type class expr, a DSL of A is going to be able to produce an F of A in that type class. And as an example here, I produce this int helper function, which returns a DSL of int, that is to say, int is the value computed by the DSL. And what it does is it simply looks up the corresponding int operation on the passed in type class called F and calls the int method on that. And what this does is it basically says this int constructor can be used to construct an integer representation over all possible representations. It is polymorphic in the type of representation. And that's a very, very powerful property. And what it allows us to do is, without support for GADs in Scala, to construct extremely type-safe code that's totally locked down, and as far as I'm aware, the Scala compiler has no bugs with this style of programming. So here's how we would interpret this DSL. We would create a new expr. In this case, I'm using ID here, which is defined up at the top. That's the identity monad. And I'm saying I'm going to construct a new expr for ID, and I'm defining all of the operations to have implementations equal to what you see. So in the case of int and stir, I just return the same thing identically. In the case of add, I add them up. In the case of concat, I concat them using string concatenation. And then I call my helper functions add and int, and I apply it to the interpreter, and that ends up building the final representation for that, which happens to be the result of the computation. So this is a totally equivalent way of building DSLs. Those are your two options for building DSLs. Either you can create a data structure and try to make that type safe using GATs, in which case you may or may not run into various compiler bugs. And then you can have helpers that construct that data structure. Or instead of building data structure directly, you can have type classes that define the operations of the DSL, which are generic in the type of thing that they compute. So you can either be sort of polymorphic on one side of the fence, which is you can have any possible way of interpreting a data structure, or you can be polymorphic in the other side, which is you're not building a data structure, but you can be polymorphic in the construction of that data structure. You can construct over all possible representations. They're competing approaches to building a DSL, and in Scala, I generally prefer the finely tagless approach. All right, so we have enough background that we can take a peek into QUARK and how it achieves its magic. Here are the building blocks for QUARK. First, type. And type represents a reified type of an element in a data set. It's not necessary, if you're building your own DSL, it's not necessary for you to create your own type system. However, it can be helpful. You can utilize Scala's own type system, and that has pros and cons. If you want to do more sophisticated things, then you're probably going to end up creating your own type system. And what that will involve doing is just defining a series of types that sort of reify the types that it is possible for your computation to create and manipulate. Dataset represents a data set that is produced by a successive series of set-level operations, like filtering something, or mapping it, or loading it from a particular location, or joining it to another data set, basically all the set-level operations. A mapping function represents a function from an A to a B that is produced by successive application of mapping level operations, for example, projecting a field in a record, or negating a numeric field in a record. Those types of mapping level operations that operate on a single element of a data set. Those are all described by mapping functions. And then finally, for reductions over the data set, like sum and average and min and max and all the different possible types of reductions, there's a reduce func which operates on an A and reduces a bunch of A's down into a B. And each one of these is described in terms of a set of operations that is applicable to that type. So for example, setops, the stuff that you can do with sets, is different than the stuff that you can do on an individual element of the data set, which is different than the stuff that you can, different than the ways in which you can aggregate a bunch of elements down to a single element. All right, let's, in our remaining 5 minutes, let's see if we can build a mini QUARK. And then you can take a look at the real source code when you have a chance. So the first thing we're going to do is build a type system. And this type system will allow us to model all the different types we want to represent in our DSL. In this case, I have everything from unknown, which represents something we have no information about. Remember, QUARK is designed for semi-structured data, so we might have a bunch of different things in here, and we may not know anything about it. All the way down to maps, arrays, tuples, booleans, integers, decimals, strings, and so on and so forth. And of course, records in QUARK are just a special case of a map, one in which the keys are strings. And now we're going to define our set level operations. This is part of our DSL that defines all the things we can do on a set. And we'll start out with a single operation here called read that says if you read from this path, you're going to get back an F. Remember, we're polymorphic in the type of representation here. So F is the representation for a set of unknown elements. This is a set of unknown elements. And based on this simple definition of setops, the first thing we need to be able to do is read. We can construct a notion of a data set. What is a data set? Well, a data set is something that if you give it a setops, any setops f, it can return you an f of a. So a data set of a is something that given a setops f can return an f of the thing that the data set holds. And given this definition of a data set, we can construct a helper function in the companion object for data set that says read from this path and return a data set of unknown. How are we going to implement that? Well, in straightforward fashion, we're just going to define the apply method, and it's going to use the read method inside of setops, which of course returns an f of unknown. Notice we haven't actually done any work here. At no point are we going to do any work. We're lazy functional programmers. We're going to describe computations. We're not going to do anything. Okay, that's one thing, but one of the most important things we can do is, if we've read from a data set, we need to be able to map over its elements and apply arbitrary changes. How are we going to do that? Well, we need something like this in setops, right? Because this is a set level operation. What goes there for f? Like we have an f of a. What goes in f? Who knows, right? You might think f of a to f of b, right? But that's not quite right. Because remember, f represents the things that you can do to a set. And the things that you can do to a set doesn't semantically make sense for the things that you can do on an individual element of a set. And this is part of why Spark is not type safe, in the sense that you can do all these things that don't make semantic sense because it doesn't lock it down enough. But we can lock it down. We can introduce a new DSL for all the things that you can do on an individual element of a set. And these things are called mapping ops. And for mapping ops, you can do things like projection. You can project things out. You can add things. You can do lengths of arrays. You can do all these different things that you can do on an individual element of a data set. And then a mapping func is simply a polymorphic over the set of all possible mapping ops. And what it does is, given an f of a, it's going to return you an f of b. So it represents a transformation from an f of a to an f of b, where f represents the capabilities of these mapping operations which apply to individual elements of a data set. All right, so with this notion of a mapping func being a transformation that uses a well-defined set of mapping operations, we can now define map in setops. And we define it like this. So map is simply given an f of a and a mapping func from or a mapping func from a to b, we can return you an f of b. All right, so here's our implementation in dataset. We know something needs to go inside the question mark, question mark, question mark. We want to be able to call dataset.map and do all sorts of interesting things with it, like we can on a Spark RDD or on a Scala collection. How are we going to do that? Well, the naive approach is, let's let f be a mapping func from a to b, right? Because then we can map the data set of a to a data set of b simply by calling the map function on the setops. The problem with that is it leads to an extremely awkward style of programming. Because remember, mapping func is not a Scala function. It's rather a trait. And it's a trait that's polymorphic in the type of representation for mapping ops. So it doesn't permit us to use the RDD and Scala collection style syntax. It's like this weird thing that's going to require people to create anonymous traits. We like to be able to do things shown at the bottom of the slide here, where I can say map every array to its length, or map every v to profits minus the losses, and things like that. That's what we want to be able to say. But we can't do that for as long as this mapping, as long as f is this mapping func. Turns out there's a really simple way to solve this problem, and that is, instead of f being a mapping func, it's actually a function from a mapping func of a to a to a mapping func of a to b. And using this solution, we can now express RDD-style operations quite naturally. We can map the arrays to their length. We can map V's to the profits minus the losses. We can treat this as if we're operating on an individual element here and using ordinary Scala syntax, including underscore notation, to build up these mapping operations. How does this work? Well, mapping functions are actually arrows. And what I mean by that is if we have a mapping function that goes from A to B and another mapping function that goes from A to C, then we can create from those two mapping functions a mapping function from A and B operate C, where operate is any binary operator. How we do that? We take the A, we feed it to the first one, then we feed it to the second one, we get two outputs from that, and we combine them using the binary operator, and now we have that mapping func from A to B operate C. So this is a very simple version of an arrow. It's actually equal to the applicative for function. It's actually the same idea behind the applicative for function. And anything more complex than this, if you try to use real arrows in Scala, it becomes monstrously hideous because arrows do compose in all sorts of really wonderful ways, but unfortunately Scala has no syntax to support them, and doing that stuff by hand is a nightmare, so I don't recommend it. But nonetheless, even this simple arrow applicative machinery allows us to construct these mapping functions from other mapping functions in a way that looks like ordinary Scala code, that gives us all the flexibility afforded by the underlying operations, but is 100% type safe, and it's constrained to only the set of operations that make sense when you're mapping individual elements of a data set. Well, time's up, so I encourage you to learn more by digging into finally Tagless. If you want a type-safe way to represent DSLs, check out that link there. Dig into QUARK at github.com, Quasar Analytics /QUARK. And finally, Quasar, which QUARK is built on top of, you can check that out at Quasar Analytics /Quasar. Thank you very much.